Welcome to the deep dive. This is where we take, well, stacks of really complex information, peel back all those layers, and boil it down to the nuggets of knowledge you actually need to be genuinely well-informed. Today, we're diving into a world that's just one of the biggest paradoxes in our solar system, Mercury.
Absolutely.
How can a planet that's basically getting blasted by the sun, practically next door to it, still be so mysterious? And honestly, how can it possibly have ice? Loads of it, apparently.
It does seem completely contradictory, doesn't it?
Totally. So we've gathered a pretty fascinating stack of sources for this. Everything from NASA's early mission reports, details from the European and Japanese space agencies, even some really old historical accounts.
It's a great mix.
Our goal today, we're going to unpack what makes Mercury, well, Mercury. We'll trace how we've observed it over time, the missions we've sent, and then get into those really big kind of speculative questions. Could humans ever go there? Is life even remotely possible?
Yeah, the really juicy stuff.
Okay, let's unpack this.
And it's so important because Mercury isn't just, another rock floating out there. Its position so close to the sun makes it this incredible natural laboratory.
A laboratory? How so?
Well, studying it helps us understand how planets form and evolve, especially planets close to their stars.
Yeah.
That tells us a lot about our whole solar system.
Right. And potentially systems beyond ours.
Exactly. It helps define the conditions, the limits, really, for where life might pop up, not just here, but on exoplanets, too. And the amazing thing is, despite being relatively close, like you said, it stayed surprisingly mysterious for a long, long time, which is why the data from recent missions think Messenger and the BepiColombo mission that's happening right now is just invaluable.
So they're filling in the gaps.
Filling gaps, rewriting textbooks.
Yeah.
It's fundamentally changing how we see the innermost planet.
Yeah.
And that knowledge ripples outwards.
Okay, so let's dive into Mercury itself, because even the basics about this planet are, well, they're not that basic.
Yeah, definitely not.
Everyone knows it's the closest planet to the sun. That's Mercury 101. And it's one of the rocky ones, right? Terrestrial, like Venus, Earth, Mars.
Correct. Part of that inner family.
But that's kind of where the easy comparisons end. It's tiny, the smallest planet in the solar system, just, 4,878 kilometers across?
Fairly wider than the continental U.S., yeah. Tiny on a planetary scale.
And if you look at pictures, especially the early ones, it looks uncannily like our moon, covered in craters.
Very much so. Heavily cratered. It really tells the story of the early solar system, all those impacts over billions of years. A shared history, in a way.
But its spin, that's where it gets really weird, doesn't it?
Oh, absolutely. Its rotation is one of the most fascinating things about it. We call it a 3.2 spin-orbit resonance.
Okay, break that down. 3 to 2.
It means Mercury spins on its axis exactly 3 times.
3 times?
For every 2 times it goes around the sun.
Okay, wait, so how does that translate into days and years?
Right. So a sidereal day, this one full 360 spin relative to the stars, takes about 59 Earth days. Pretty slow.
59 days for one rotation.
Okay, but a solar day sunrise to the next sunrise at the same spot, that takes a whopping 176 Earth days.
176?
Yep, which is exactly twice the length of its year. Its year is only 88 Earth days long.
So you wait almost 6 Earth months for the sun to come up again. That's bizarre.
Completely bizarre, imagine that. And figuring this out was a huge aha. People used to think it was tidally locked, like our moon, 1-to-1.
Ah, right. Always showing the same face to the sun.
Exactly. But radar data in the 60s proved that wrong. And it was an Italian mathematician and engineer, BepiColombo, everyone called him Bepi, who figured out the 3.2 resonance in 1965.
BepiColombo. Like the mission.
Precisely. The mission's named after him. He was brilliant.
Yeah.
He also came up with the idea of using a gravity assessed from Venus to get Mariner 10 to Mercury.
The slingshot maneuver.
A slingshot maneuver.
Yeah.
Crucial. His insights basically opened the door to exploring Mercury. A well-deserved namesake.
So the super slow rotation, plus being so close to the sun, that leads to crazy temperatures, right?
Oh, the most extreme temperature swings in the entire solar system. Nothing else comes close.
Okay, hit me with the numbers. How hot does it get?
During that long day, the surface can hit 430 degrees Celsius. That's 800 Fahrenheit.
430 C. Hot enough to melt lead?
Lead, zinc. Yeah, literally melt metal on the ground.
Okay, but here's where it gets really interesting. The night side must be freezing then.
Freezing doesn't even cover it because there's almost no atmosphere to hold the heat in, and the rotation is so slow. Once the sun sets, temperatures plummet. down to minus 180 Celsius. That's minus 290 Fahrenheit.
Minus 180 C. So from plus 430 to Lena 180, that's a swing of
Yeah.
over 600 degrees Celsius.
Over 600 degrees. Yeah, it's just mind-boggling. Imagine trying to design something,
Yeah.
anything, to survive that.
A spacesuit for that. Forget it.
Exactly. And the main reason, like I said, is the lack of atmosphere. No blanket to trap heat, no winds to spread it around.
So heat just radiates straight out into space.
Yeah, instantly. As soon as the sun's gone, it gets incredibly cold, incredibly fast, and stays that way for, almost 3 Earth months.
But it's not the hottest planet overall, right? That's Venus.
Correct. Venus holds that title. Its super thick carbon dioxide atmosphere creates a runaway greenhouse effect.
So Venus is just hot everywhere, all the time.
Pretty much around 464 Celsius, day or night. Insanely hot, but consistent. Mercury, though, it's the planet of extremes. Hot side, cold side. Shows you how critical an atmosphere is.
Okay, let's zoom in on the surface itself. We said it looks like the moon, very cratered.
Definitely.
Yeah.
But it has its own distinct geology, its own story written on the surface.
Yeah.
Broadly, you can divide it into, say, 3 types of terrain.
Okay.
You've got the really old, heavily cratered terrain, classic bombardment scars. Then there are the intercrater plains. These actually cover something like 70% of the surface we've mapped.
70%. So
Right.
something smoothed things out.
Seems like it. Possibly early volcanic activity filling in older craters. And then you have even smoother plains, which look even more like ancient lava flows, maybe filling huge basins.
Speaking of huge basins, Caloris, that's the big one.
The biggest one we know of, the Caloris Basin. It's immense, 1,550 kilometers across.
1,500 kilometers. That's enormous. Texas-sized, you said.
Roughly, yeah. And the impact that made it was unbelievably violent. It didn't just dig a hole. It triggered massive lava eruptions nearby.
Wow.
And it threw up this ring of mountains around the edge about 2 kilometers high. Scientists are still debating if the floor's impact melt or later volcanic flows. A truly cataclysmic event.
And didn't that impact cause something weird on the other side of the planet?
Yes. The perfectly named weird terrain.
Love it.
It's this chaotic, hilly, grooved landscape directly opposite Caloris at the antipode.
So how did it form?
The leading idea is that the seismic waves from the Caloris impact traveled through the entire planet. Through the core, converged on the far side, and basically shattered and jumbled across there. Imagine hitting a ball bearing so hard it ripples on the other side.
Shaking the whole planet. Incredible.
Then you have the features that are maybe most characteristically Mercury. The Lorbade scarps.
Lorbade scarps. Okay, what are they?
Think of them as giant wrinkles or cliffs. Hundreds of them, curving across the surface, some hundreds of kilometers long, and up to like a mile high.
Wrinkles. How does a planet get wrinkles?
It's shrinking. As Mercury's huge iron core cooled over billions of years, it contracted. The solid crust on top had nowhere to go.
So it buckled.
It buckled and crumpled, yeah, thrusting up over itself along these fault lines. These scarps are basically massive thrust faults, and they're everywhere, globally distributed.
Which tells us?
It tells us the whole planet has shrunk. Estimates are its radius might have decreased by as much as 7 kilometers since it formed. It's literally a shrinking world.
Wow. Still shrinking now.
Probably. It seems to be an ongoing process. And one more recent discovery, really intriguing, are the hollows.
Hollows.
Yeah, these unique, shallow, sort of bright, irregularly shaped pits, often found inside craters. They're unique to Mercury.
And what makes them?
We think it's sublimation.
Well,
Volatile materials, the stuff that turns straight from solid to gas, buried just under the surface, get exposed by impacts, maybe, and they just vaporize away in the heat and vacuum, leaving these hollows.
sublimation. Like dry ice?
Kind of, yeah.
Yeah.
It suggests that there might be more volatile stuff hidden in Mercury's crust than we thought. It's not just inert rock. There's active geology happening, even now.
Fascinating. So not just a dead rock at all.
Definitely not. Even its atmosphere, or lack thereof, is dynamic.
Right, you said it doesn't really have an atmosphere like Earth's. It's an exosphere.
Exactly. An exosphere. It's incredibly thin, just this tenuous veil of individual atoms and plasma. Not dense enough to breathe, or trap heat, or cause weather.
What's it made of?
Mostly things knocked off the surface by sunlight and micrometeoroids, or sputtered by the solar wind. We see hydrogen, helium, oxygen, sodium, potassium, calcium, bits and pieces.
So it's constantly being lost and replenished.
Constantly. It's not stable. Atoms escape into space, and new ones get kicked up from the ground, or delivered by the solar wind.
Ah, the solar wind. That must have a big effect so close to the sun.
Huge effect. It's constantly bombarding the surface and stripping away the exosphere. It shapes the whole environment.
And despite that, and the slow rotation, Mercury has a magnetic field. That was a surprise, wasn't it?
A massive surprise.
Yeah.
When Mariner 10 detected it, it really threw planetary scientists for a loop.
Because slow rotation usually means no dynamo, no magnetic field.
Generally, yes. The thinking was it wouldn't have the necessary churning in its core, so finding one was remarkable. It's the only other terrestrial planet besides Earth with its own global magnetic field.
But it's much weaker than Earth's.
Oh yeah, tiny in comparison, about 100 times weaker, only about 1% of Earth's strength.
And it's off-center.
Very much so. That was a key finding from Messenger. The magnetic equator is shifted way north of the geographic equator by about 484 kilometers.
484 kilometers. That's a big offset, almost 20% of its radius.
Exactly. It's a huge tilt. We're still trying to figure out exactly why that is.
So why does this weak offset field even matter?
Well, first, the fact that it exists tells us there must be liquid, circulating material in its core generating that dynamo, probably its large, iron-rich outer core.
Kept liquid by tidal forces because of its weird orbit.
That's part of the theory, yeah. Strong tidal squeezing from the sun due to its eccentric orbit probably helps keep that outer core molten. And even though it's weak, the field does deflect the solar wind.
Creating a magnetosphere.
A mini magnetosphere, yes. Small enough to fit inside Earth's. But it's there. And the interaction is really dynamic.
Dynamic how?
The magnetosphere traps some solar wind plasma, and that plasma bombards the surface, causing space weathering. And we see these things called magnetic tornadoes.
Magnetic tornadoes, seriously.
Seriously, they're like twisted ropes of magnetic field lines, flux ropes that connect directly from space down to the surface.
And they funnel.
Yeah.
What?
Hot, fast-moving plasma from the solar wind straight onto the ground.
Ouch. That sounds nasty.
It is, and it's fundamentally different from Earth. Here, our magnetic field lines connect to our ionosphere, high up. On Mercury, because there's no real atmosphere or ionosphere,
They connect right to the rock.
right into the regolith, the surface soil. It's a direct electrodynamic coupling. Solar wind particles can basically follow these magnetic pathways right down to impact large areas, especially near the poles.
So the ground itself is part of the circuit.
In a way, yes. Understanding how those currents close in the surface, not an ionosphere, is a big research question. Very different from Earth.
Okay, magnetic tornadoes. Shrinking planet. But maybe the most surprising thing is the ice, right? Water ice on Mercury.
That was, and still is, one of the most counterintuitive discoveries. Finding water ice on a planet hot enough to melt lead.
Seems impossible, like finding a snowball in an oven.
Exactly. But radar observations from Earth first hinted at these bright patches in polar craters, regions that are permanently shadowed.
Because the sun never shines directly in them.
Right. Due to Mercury's tiny axial tilt and the high crater rims, sunlight never reaches the floors of some craters near the poles. They're perpetually dark and incredibly cold.
And Messenger confirmed it was ice.
Definitively, Messenger confirmed these radar-bright deposits are abundant water ice. And not just pure ice either.
What else is there?
It's mixed with some kind of dark, organic-rich material.
Organic, like carbon compounds, building blocks of life.
Precisely. The very building blocks. So what does this all mean? It's profound.
Yeah, what does it mean?
Well, first, the neutron spectrometer on Messenger suggested the ice isn't just sitting on the surface. It's buried maybe 10 centimeters down, insulated by a layer of that dark stuff.
Insulation. That helps.
Critically, it protects the ice from sublimation and a little bit of scattered light or heat. Finding water and organics, the precursors to life, in one of the hottest neighborhoods of the solar system. That just blew traditional ideas about Mercury out of the water.
Changes the game completely.
Totally. It suggests resources might be there, hidden away. And it forces us to ask much deeper questions about habitability itself, even in such extreme places.
So how did we even start figuring all this out? Observing Mercury from Earth sounds like a nightmare.
It was, and still is, incredibly challenging. It's so close to the sun it's usually lost in the glare.
You can only see it just after sunset or just before sunrise, right? Low on the horizon.
Exactly. Very brief windows. Makes it really tough to get good, steady observations.
Who were the early pioneers trying to map it?
Well, back around 1800, a German astronomer named Johann Schroeder made some early sketches. He famously thought he saw mountains 20 kilometers high, which wasn't quite right.
Yeah. Understandable error, maybe, given the difficulty.
Absolutely. Then, in the 1880s, the Italian astronomer Giovanni Schiaparelli did much better. He made more accurate maps and was the first to suggest its rotation was slow. He thought 88 days, tidally locked.
Close, but not quite the 3.2 resonance.
Right, but a huge step forward from thinking it spun quickly. His idea of tidal locking was the prevailing theory for decades.
And someone else refined the maps later.
Yes, Eugenius Antoniadi, a Greek astronomer, published a really detailed map in 1934. He used a large telescope in France. Many of the surface feature names we use today come from his maps, those light and dark patches called albedo features.
So these oath-bound astronomers, despite the challenges, they laid the groundwork.
Absolutely crucial groundwork, painstaking work. Yeah. It built up this picture, however incomplete, that really fueled the desire to send spacecraft there.
Which brings us to Mariner 10, the first robotic visitor.
The Trailblazer, Mariner 10, launched by NASA JPL in November '73. An absolutely revolutionary mission.
Revolutionary how? What were its firsts?
Oh, it had a bunch. First spacecraft sent to Mercury, obviously. First to use a gravity assist from one planet, Venus, to reach another that was BepiColombo's idea, brought to life by Michael Minovich's calculations.
The Venus slingshot. Got it.
First mission to explore two planets, Venus and Mercury, on one trip. First to return to its target, making 3 Mercury flybys.
3 flybys! Wow.
Yep. Closest approach was just 327 kilometers. And another first. It even used the pressure of sunlight, the solar wind, to help control its orientation. Clever stuff to save fuel.
And its biggest discovery was the magnetic field.
That was the headline discovery, yes. Totally unexpected at the time. It also detected energetic particles, but they couldn't quite figure out what they were with the instruments back then.
So it gave us our first real close-ups.
Our first glimpse of that cratered surface, Caloris Basin. It showed us a world far more complex than imagined. Though it had its problems too, apparently its temperature control wasn't perfect. Sometimes it would start tumbling.
Space exploration is never easy.
Never. But they managed those 3 flybys, got incredible data back.
But flybys only give you snapshots. We needed an orbiter, right?
Exactly. We needed long-term observation. And that's what Messenger delivered.
Messenger, Mercury surface, space environment, geochemistry, and ranging. Quite the mouthful.
Oh. Yeah. NASA loves its acronyms. Launched in 2004. Took a long, winding path.
More gravity assists.
Many. Earth, Venus, Mercury itself. Finally went into orbit around Mercury in March 2011.
And stayed there for how long?
4 years. 4 years of continuous observation before they deliberately crashed it onto the surface in 2015 when it ran out of fuel.
4 years must have generated a mountain of data.
Absolutely revolutionized our view. It gave us the first complete, high-resolution global map. Finally saw the half of Mercury Mariner 10 missed. Revealed all sorts of features, like those hollows.
And it helped figure out the inside of the planet, too.
Yes. By precisely tracking its spin and gravity, Messenger's data showed Mercury has a solid inner core inside its liquid outer core. Big deal for understanding its formation.
And it confirmed the ice and organics.
Confirmed them beyond doubt with its spectrometers. Solved that mystery. It also figured out those energetic particles Mariner 10 saw were electrons.
Clearing up old questions?
Exactly. And it mapped that offset magnetic field in detail, studied the magnetic tornadoes, the whole interaction with the solar wind. It was the comprehensive survey Mercury desperately needed.
Which leads us to the mission that's out there right now, BepiColombo.
The current state of the art. A joint mission, European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA.
Named after the man himself.
A fitting tribute. And it's unique because it's 2 spacecraft flying together.
2? Okay, what's the setup?
You have ESA's Mercury Planetary Orbiter, MPO, which will orbit close-in, focusing on the surface and interior. And then you have JAXA's MEO, Mercury Magnetospheric Orbiter, MMO, which will be in a different orbit, specifically studying the magnetic field, the exosphere, the whole space environment.
2 perspectives at once. Clever.
Extremely clever. Essential for understanding dynamic processes.
So what are BepiColombo's main goals? What mysteries is it trying to solve?
It's aiming for a really deep understanding. How did Mercury form and evolve so close to the Sun? What's its exact internal structure and surface composition? How does that thin exosphere work and interact with the solar wind? Where does the magnetic field really come from?
Through confirming the dynamo theory.
Testing it rigorously, yes.
Yeah.
And mapping the magnetosphere in unprecedented detail. Plus, it's going to do a super precise test of Einstein's general relativity.
Wow.
By measuring the tiny shift in Mercury's orbit over time, the precession of its perihelion. It was one of the first proofs of relativity, and BepiColombo will measure it more accurately than ever before.
Wow, okay. And basic stuff, too, like why is Mercury so dense?
Exactly. Why the huge iron core?
Yeah.
And what's the deal with polar ice, its origin, its exact composition? BepiColombo has the instruments to tackle all of that.
Getting there must be even harder now, aiming for specific orbits.
Oh, the journey is incredibly complex.
Yeah.
Launched in 2018, it's not scheduled to arrive in orbit until late 2026.
2026, that's an 8-year trip.
Roughly, yeah, longer than initially planned. It's doing this intricate dance of gravity assists, 1 Earth flyby, 2 Venus, and 6 Mercury flybys.
6 Mercury flybys just to slow down enough.
Exactly, shedding orbital energy bit by bit to let Mercury's gravity capture it. It also uses solar electric propulsion ion thrusters.
Ion drives, like in sci-fi.
Pretty much, they use solar power to accelerate xenon gas, providing a very gentle but continuous thrust over a long time. BepiColombo's system is the most powerful one ever flown interplanetary.
Gives it a lot of braking power, essentially.
Huge braking and maneuvering capability, yeah. Saves enormous amounts of conventional fuel.
And have these flybys already produced results?
Oh, yes. The Earth flyby let them test sensitive instruments by detecting the crossing of our magnetosphere. The Venus flybys involved coordinated science with other probes orbiting Venus.
Teamwork.
Definitely. And the Mercury flybys are already giving us amazing close-up images and data, sampling regions they won't reach once they're in their final orbits. Little sneak previews. One flyby got within 200 kilometers.
Just surviving that close to the sun must be an engineering nightmare.
It's brutal. Solar radiation is 10 times stronger than at Earth. They had to basically reinvent material science for BepiColombo. Something like 82% of the hardware was developed from scratch.
82%. That's staggering.
It really is. Take the solar panels. Normal ones would melt. These use special carbon fiber, new adhesives, and they have to tilt them up to 70 degrees away from the sun just to survive over 200 Celsius.
Angling them so they don't get the full blast.
Exactly. And the heat shield. It's a multi-layer marvel. Ceramic cloth, aluminum, special plastics like Upalex and Mylar, dozens of layers thick, all to reflect and radiate away that intense heat.
Like a high-tech thermos.
A very, very high-tech thermos.
Yeah.
They even had to modify Europe's biggest vacuum chamber to simulate Mercury sunlight levels for testing. Just an incredible feat of engineering.
All to protect the instruments. What kind of gear are the 2 orbiters carrying?
A whole suite. MPO has 11 instruments. MEO has 5. Cameras, spectrometers across the spectrum, infrared, UV, X-ray, gamma ray, neutron radiometer, laser altimeter, magnetometers, particle detectors.
Basically everything you'd need to study every aspect of the planet.
Pretty much. From the core to the surface, the exosphere, the magnetic field, the works. And having 2 spacecraft is key for the magnetosphere stuff.
Right, the simultaneous measurements.
Seeing how the field and solar wind interact from 2 different points at the same time, that gives you a 3D picture you just can't get with one observer. Crucial for understanding those dynamic processes like the tornadoes.
It's amazing what's flying out there, but wasn't there supposed to be a lander originally?
Ah, yes, the forgotten part of the mission. There was a plan for a Mercury surface element, MSE lander.
What happened to it?
Budget cuts, sadly. Canceled back in 2003. It's a common story in space exploration.
Shame. What was it supposed to do?
It was designed to be small, only 44 kilos, disc-shaped. It would have landed near the Terminator, the day-night line, where it's a bit cooler.
Using airbags.
Yeah, braking, ejecting its propulsion, then airbags for the final impact. Pretty ambitious.
And what science would it have done?
It had cameras, a heat probe, spectrometers, magnetometer, seismometer to listen for mercury quakes, even a little burrowing mole, and potentially a tiny rover.
A rover on Mercury, wow.
It would have been amazing. Direct ground truth measurements, a real lost opportunity. But it highlights just how incredibly difficult and expensive it is to get to Mercury, let alone land and operate on the surface.
Which naturally leads us to, could humans ever go? We've been to the moon, we're planning for Mars, but Mercury seems like a whole other level of impossible. It really is formally in the realm of science fiction for the foreseeable future. It's not just distance or time, it's that trifecta of challenges, as you put it.
Okay, remind us, challenge 1, the temperature extremes.
430 C day, minus 180 C night, massive rapid swings.
Brutal. Challenge 2, no atmosphere.
Which means no aerobraking for landing. You need colossal amounts of fuel to slow down. And critically, no protection from raw solar radiation.
Lethal radiation levels at sunrise. Instantly lethal if you're unprotected. Burns you to a crisp.
And challenge 3, well, maybe less critical, but the view wouldn't even be that interesting. Boring sunsets.
Hey, aesthetically, yeah. No atmosphere means no scattering of light. The sun would just be this incredibly bright disk dropping below a pure black horizon. Very stark, very alien.
So landing humans there, incredibly difficult. But didn't NASA have a Project Mercury back in the day?
Ah, good point to clarify. Yes, Project Mercury was NASA's first human spaceflight program, early 1960s. Alan Shepard, John Glenn.
Right, the first Americans in space.
Exactly. But it was all about just getting humans into Earth orbit and back safely. Testing if people could function up there. It had absolutely nothing to do with the planet Mercury. Just shared a name.
Okay, important distinction. Did they learn anything from Project Mercury relevant to going to other planets?
One interesting biomedical finding was that things like increased heart rate, weight loss, blood pressure changes, they correlated more with how long the astronauts spent sealed inside their suits than just time and space.
So just being cooped up in the suit was stressful.
Very stressful on the body, even for relatively short flights in Earth orbit. Now imagine trying to live and work in a suit or a habitat under Mercury's conditions.
Yeah, magnifies the problem immensely. If just being in a suit near Earth was tough.
Doing it on Mercury,
Yeah.
with the radiation, the temperature swings, the isolation, it highlights how fundamentally hostile that environment is to human physiology.
Okay, so human visits are probably off the table for a long, long time. What about life? Could anything live there?
Traditionally, the answer was a hard no. Just a baked, sterile rock, too hot, too much radiation, no atmosphere to speak of,
Yeah.
seemingly impossible for life as we know it.
But the ice
Yeah.
and the organics, that changed things.
Radically altered the perspective. Finding the basic ingredients, water and complex carbon compounds in those permanently shadowed craters was huge.
It means the building blocks can survive there.
They can persist. And it leads to this idea of potentially habitable niches, not on the surface, but below ground.
Subsurface habitats.
Exactly. There's even speculation about salty subsurface glaciers. The key is finding locations shielded from the extremes.
Like the floors of those polar craters.
Precisely. Thermally, they're the most stable places on the planet, perpetually cold. And if you go just a little way underground,
That 10 centimeters or so of soil provides insulation.
perfect amounts of soil could create insulation, potentially maintaining stable, moderate temperatures below maybe even Goldilocks temperatures, where salty water could remain liquid.
Liquid water below the surface of Mercury. Wow.
It raises an important question, doesn't it? It forces us to rethink habitability. Maybe it's not just about the habitable zone distance from a star, but about these protected microenvironments. Life could be hiding away.
Like extremophiles on Earth finding weird niches.
Exactly like that. Hiding in the dark, shielded from the surface inferno. It's a fascinating possibility. Science fiction has played with similar ideas, like Kim Stanley Robinson's moving city concept.
The city on rails at the Terminator.
Yeah, always staying in the twilight zone. It shows how we grapple with surviving such extremes, even imaginatively. It broadens our definition of where life might hang on.
What an amazing arc of discovery.
Yeah.
From blurry telescope views to BepiColombo sending back data right now, Mercury's turned out to be so much more than just a hot rock.
So much more.
It's so-
Dynamic, complex, shrinking, magnetic, icy. It holds so many clues.
Clues about how planets form near stars, how they interact with solar wind.
And maybe clues about where life's ingredients can survive against all odds.
Yeah, that last point. If the
Yeah.
stuff of life can exist on Mercury, in those hidden pockets.
What does it say about other seemingly hostile places? Under the ice of Europa, deep
Uh,
below the surface of Mars, maybe even on scorching exoplanets.
it suggests habitability might be more widespread, just
Mm.
hidden.
It certainly pushes us to look in places we might have previously dismissed. Mercury's secrets force us to keep an open mind. There's always more to learn, always more surprises waiting.
Absolutely. A fantastic reminder that even the most familiar seeming corners of our solar system can hold incredible mysteries. We hope this deep dive has sparked your curiosity about Mercury and maybe encourages you to keep exploring, keep questioning, and keep diving deep into the universe around us.